Doctor, you're rolling. You may proceed, sir.
Thank you so much. We are continuing our discussion, and we are asking the following question to ourselves. What is our topic number, first of all? $18. So, zero frequencies possessed by a free beam. So past time we saw that simply supported free beam has zero frequency. So there is this zero frequency. And it is associated with the possibility of such a movement of this beam, just rotation, without any deformation, no deformation. It moves like a rigid body. This beam moves like a rigid body, rotates, and this is actually corresponds to natural frequency, or first natural frequency equals 0. Then there is, of course, second natural frequency, etc. Now we would like to ask the following question, whether or not free beam has zero natural frequency. Now, zero natural frequency actually means that, look please, we have this governing differential equation is EI d4w dx in force power plus rho a d2w dt square. This equals 0. Small w then equals capital W of x times cosine omega t. This is omega. This is w. This is displacement. This is the frequency. Then we substitute this back, we get EI, force derivative of capital W with respect to x, then times cosine omega t, minus. So when I differentiate with time, it will be omega square, then rho a, W, cosine omega t. This equals 0. I can take out cosine omega t. What is left is EI, force derivative of W with respect to x, minus a omega square W. That equals 0. Okay? Am I too fast? Yes? No? No. So therefore, this expression in parentheses must equal 0. Or EI, force derivative with respect of W with respect to x, minus rho a omega square W should be 0. And zero frequency means this term is 0, because omega is 0. So therefore, I have this force derivative of W with respect to x equals 0. So therefore W is a fourth order polynomial. That is a1 plus a2 plus a3, a2x plus a3x squared plus a4x cubed. So that is a mode shape. Mode shape is polynomial. Okay, are you writing this? Now I have to satisfy the boundary conditions. So it is a free beam, means secondary bending moment equals 0 and shearing force equals 0 at x equals 0 and x equals L. So we calculate the first derivative. Will be a2 plus 2 times a3 from here. 2 times a3x plus here x cubed. 3 times a4x squared. Then I differentiate again. W second derivative will be 2 times a3 here from this term plus 6 times a4x. And I differentiate once again. I am getting third derivative equals 6 times a4. Now, because W's third derivative equals 0 at 0, a4 must vanish. A4 must vanish. But a4 equals 0 means a4 equals the third derivative. That means that third derivative at L is also 0, because if this term is 0, then third derivative is 0 everywhere, for every x, because there is no x here. So therefore, we automatically, that is AUT, automatically satisfy the other condition also. Third derivative at L. So then, because a4 equals 0, we are left only with 3 constants. Okay. Now we go to W second derivative. Okay, this is a second derivative. Second derivative, we had 2 times a3 plus 6a4 x, but this equals 0. So we go to the second derivative. Second derivative at x equals 2 times a3. So if a3 is taken 0, then we satisfy boundary condition for W second derivative. So W second derivative at x equals 0 for any x. So boundary conditions are automatically now satisfied. A3 equals 0, A4 equals 0. So again, I wrote this sentence. A3 equals 0, A4 equals 0 means that all boundary conditions are automatically satisfied. But this means that we are left with 2 constants, a1 plus a2x. W of x equals a1 plus a2x. Now, this expression satisfies all boundary conditions. It satisfies all boundary conditions. Now, so there are 2 cases here when we have a1 and a2. a2 equals 0, but a2 equals 0, but a1 is not 0. Let me put this one on the answer. A2 equals 0, A1 is not 0. This is Beam's translation, or just displacement as a rigid body. You may want to write down. Translation and just movement as a rigid body are the same things. So then A1 equals 0, but A2 is not 0. A1 is 0, but A2 is not 0. This means that it's a rotation. Because, look please, it rotates at various axes. There is a different value of W. So it just, in the beginning it's 0. And in the other places it's proportional to x. So that is a rotation. So actually what happens is as follows. That natural frequencies of this beam are 0, 0. So this beam has 2 0 natural frequencies. So that is translation, this is rotation. And then come natural frequencies that are associated with clamped beam. One can show that the same characteristic equation is obtained. Okay. What is our homework set? Say it again. 10. Okay. So let us write it down. Set 10. 1. Show that FF and clamped beams have the same characteristic equation. I think CC equals 1, I think. Clamped, I think if you check, it is CC equals 1. Cosine alpha L. Please check this. Cosine alpha L, hyperbolic cosine alpha L equals 1. I think that is an equation. So look please, if for free beam we get the same equation, that means that we have the same roots. But in addition to these roots, we also have 2 more roots. Okay? So free beam as if has infinity plus 2 natural frequencies, if you want. We can put it in such an interesting manner. So we have this here is infinite amount of frequencies and plus 2, which means infinite, of course, infinite number of frequencies. Okay, this we don't need, the rest we don't need. Or, okay. Any questions here? No. Now we will go to the following topic, which is 19. And that has to do with vibrations in presence of axial load. Okay. So imagine we have this beam that is simply supported here, roller support here, and there is also P here. The length is L, and it vibrates, etc. So without P, we know the differential equation. EI d4W dx in force power plus rho A d2W dt square. With P, but no vibration. So differential equation is like this. EI d4W dx in force power plus P d2W dx square equals 0. Okay? In this case, if there is no vibrations, then W is a function only of x. Here, W is a function of x and t, so therefore, partial derivatives. here direct derivative. So let us call this problem star, this problem double star. And then there is triple star, if you want. And that is vibration P included. And that will be like this. EI, first derivative of W with respect to X, plus P, second derivative of W with respect to X squared, plus rho A d2W dt squared equals 0. So this we know how to solve, the first star problem. We dealt until now. Yes, we know this. Okay, until now we were dealing only with this. Now let us just remind you, remind you what happens in double star. So there is no vibrations, but just there is axial load. So let us recall this. Okay? And so what we have here is as follows. Let us subtopic, yes, subtopic. Buckling of a column. Okay? And buckling of the column is like this. So we have EI, first derivative of W with respect to X, plus P d2W dx squared equals 0. Okay, we consider simply supported column. So if a beam is under axial load, it is called a column. Okay, so this is a column. Then what we do is as follows. We would like to find W. Now, what happens is as follows. We do some experiment. Experiment is as follows. Look, please. I take this column. First, I don't put any load on it. And then I give some small kick. Now, what does it mean? I give a small kick, then I'm removing small kick. So when I give a small kick, this column deflects. Then I'm removing the kick. Then column returns to the original position. Returns to the original position. Then I'm increasing the load. So I put some P1. So P1 is greater than 0. Again, I give a kick. Then I'm so as a result, this column deflects. Then I'm removing the kick. This column goes back to the original position. So goes back. Then I'm increasing my load. Okay? And I'm giving a kick, etc. So we are doing this experiment until we are getting to some position. So this P equals P critical, such that there is some small kick, but the column does not go back into the original position. Okay, so does not go back means lost stability. It lost stability. Okay, or we call it losing stability means buckling. Okay, so we want to find this P critical. Okay, why do we want to find? We know that we want to stay away from P critical. Why? Because at this point, if there is some small kick, then system actually never comes back to its original equilibrium position. This is not unlike human relationships when some people are sometimes exhibiting instability, means just small word, maybe not well calculated word, can bring to a very big reaction from a person, from the other person. So then we say that that person is not in a stable state, so to say. Yes, sir. Does not go back means he stays there. I mean, you gave a kick, it gets bent, and it does not go back. When you remove the kick, it did not go back. You gave a kick like this, and it bent, but then I removed it, it comes back. It comes back for various P's, but when P equals P critical, it does not come back. So then it loses property of being restored. I increase the load, P. I increase every time P, and I'm getting to this position. So that value, when this happens, is called P critical. Okay? So we want to stay away from P critical naturally. So how to find it? So what we want is find P critical. What is P critical? Okay, at P equals P critical, W of X does not equal automatical 0. So that is what P critical means. That is what we just defined. We said W does not come back. W equals 0 at the endpoints, but it does not equal 0 everywhere. If it equals 0 everywhere, then it is in straight position. Okay? Again, W equals 0 at X equals 0 and X equals L, but not everywhere. Straight position of equilibrium has been lost. Okay? So we have this EI d4W dx in force power plus P critical W equals 0. P d2W dx square equals 0. Okay. Now, we divide by EI. I get d4w dx squared plus p critical over EI. d2w dx squared equals 0. Here is a fourth derivative. Here is a second derivative. When I differentiate this 4 times, I will get expression in the fourth power. Here, however, I will get in the second power. So therefore, it makes sense to call it alpha square. Okay, no, beta square, because we had alpha. Beta square equals p critical over EI. Okay, so I have w fourth derivative plus beta square w second derivative equals 0. This is my equation. So I substitute w equals c in power rx. I get r in fourth power plus beta square r square equals 0. Then I get from here r square can be taken out. R square plus beta square equals 0. Or I have R1, 2 equals 0. R3, 4 equals plus minus I beta. Okay, then what we get is as follows. This is page 4. What we get then is as follows. This is fine. W equals C1 plus C2x plus C3 sine beta x plus C4 cosine beta x. Okay. Now I have W at 0 must, so these are boundary conditions. W at 0 must equal 0. So we get C1, this is multiplied, this is also, plus C4 equals 0. Then first derivative will be C2 plus C3 beta cosine beta x minus C4 beta sine beta x. W second derivative equals, okay, C3 minus C3 beta squared sine beta x minus C4 beta squared cosine beta x. So at 0, this must be 0. So this is 0 anyways, because sine beta, so therefore C4 equals 0. But we had C1 plus C4 equals 0. Therefore, C1 is also 0. So therefore, W of x equals C2x plus C3 sine beta x. Okay? Now W at L equals 0. So C2L plus C3 sine beta L must equal 0. And second derivative at L must equal 0. Second derivative at L means this one. This is the second derivative. This one, C4 is 0. So that is C3 beta squared sine beta L equals 0. Okay, now let us consider beta. Beta, of course, is not 0, because beta equals square root of P critical over EI. We said that P critical is not 0. So remember, we had it zeros, and we increased, and we increased, and we increased. So P critical is not 0. So beta is not 0. So we can divide by beta square, the last equation, this one. So I will get then C3 sine beta L equals 0. Okay, I substitute this here. We substitute this in the previous equation. C3 sine beta L equals 0 into that equation. So we get then C2 equals 0. So that means that, look, C1, C2, C4 equals 0. Vanish. Okay, so we are here. We have C3 sine beta L equals 0. So there are two possibilities. C3 equals 0 and sine beta L equals 0. Am I going too fast? Too fast? Okay, then I will wait. Because this expression equals 0, then C2L must be 0. L is not 0, so C2 equals 0. So we are left with C1, C2, and C4 are vanishing. So we are left only with C3. So, and this is an equation. C3 sine beta L equals 0. So when product equals 0, then either factor equals 0 or maybe both equal 0. So there is a possibility that C3 equals 0 or sine beta L equals 0 or both equal 0. Now, C3 cannot equal 0. I will tell you why. C3 is not 0. Why? Because otherwise, C1, C2, C3, C4 would be 0. And hence, W of x would be everywhere 0. Because there are 4 constants. C1, because W of x equals C1 plus C2x plus C3 sine beta x plus C4 cosine beta x. So C3 is not 0. So we are left with sine beta L equals 0. Sine beta L equals 0. Now that means that beta L must equal 0 or pi or 2 pi or 3 pi, etc. N pi. Okay, n is a positive integer. Now let us consider all these possibilities. Beta L cannot equal 0, this one, because otherwise beta equals P critical over EI. And if it equals 0, that would mean that P critical equals 0. This contradicts experiment. Contradicts our experiment. We said the experiment that P is increasing and etc. So therefore the first possibility for beta is beta L equals pi, or beta equals pi over L. Now, but beta equals square root of P critical over EI. Write it down. So that is a definition, is it not? Definition. So from here we can, if we square both, square these quantities, we will get pi square over L square equals P critical over EI. So from here we get P critical. P critical equals pi square EI over L square. Okay? So this formula was derived by Euler, 1744. Okay. Was written by Euler. He did not derive, just wrote a formula. And by Lagrange, 1783. So he gave a derivation. Okay. First one is from Switzerland. This is from France. It's from French. Okay. Now that means that if P critical, if this load equals pi square EI over L square, then small kick would result into non-return, first of all, bending and non-return to the original position, or buckling. So this is called buckling load. Now let us just, we want also to find W of x. So W of x, if you remember, was C1 plus C2x plus C3 sine beta x plus C4 cosine beta x. Yes. And then these guys are 0. So W of x equals C3 sine beta x. But beta equals, we found beta. Remember, pi over L. So that is C3 sine pi over L times x. So that means that, look please, that is this beam. So that is sine pi x over L. So this is like this, this is, so here the function is like this. That is called buckling mode. Buckling mode. So let me give you a second homework. Obtain the buckling load for a clamped beam, clamped column. Okay, did we write? So this is a buckling mode. paying attention, W of x is determined up to a constant C3. So C3 is not 0 and not determined. So we only know C3 is not 0. Page 7. Any questions up to now? Yes, sir? Okay, so there was a question, 7, 8. So question was posed, why not to use n pi, where n is a positive integer? Answer, we certainly can use n pi, not just pi. We will get the following. P critical equals n pi square over times ei over L square. And W of x equals C3 sine n pi x over L. Okay? So where n equals 1, 2, 3, etc. Because I said I brought first, I dealt with first just. For example, if n equals 2, then this is happening. If n equals, that is this. If n equals 3, then this is happening, etc. So a question, can a column buckle at, so this is called second buckling mode. That is third buckling mode. Question, can a column buckle at the second mode? This mode. Answer, yes. You see, when I talked about kicks, so if someone gives such a kick and then here this type of kick, you know, the two people are standing. The kicks can be arbitrary. Kicks can be arbitrary. So if we give such a kick that first mode cannot occur, then second mode may occur. So if I give such a kick, say in 1/4 here and 1/4 from there, then this will come there. Okay? And buckling load will be, appropriate buckling load, P critical, will be 2 pi squared EI over L square. Or P critical equals 4 pi square EI over L square. Means 4 times more. Four times more. Second buckling load is 4 times more than the first buckling mode. Any questions? Can a column buckle at the second mode? So that was a question by a student. The answer is yes. Yes, third question. Yes. Yeah, I mean, naturally look, in the nature, of course, such kicks do not occur. I mean, look, please, if there is some small wind, we would ask the wind, can you come, when you come, can you come in such a manner that you will concentrate 1/4 on the top and 1/4 on the bottom and go in opposite directions? Can you have such a wind? If that wind will be very beneficial for us, because buckling load increases 4 times, means that load can increase and increase. But usually such things do not happen. We do not have a communication of such a direct communication with nature. Therefore, we should take into consideration the first possibility of buckling. First possibility of buckling is the first load is already dangerous. If the kicks are this type, then yes, this value is dangerous. The rest of the values are not dangerous until there. Okay? If the kick is of very special kind, then yes. But this, of course, doesn't. In experiment, one could have this. One could specially maintain such things that we will give specific kicks and system will buckle like this. Yeah, that could be done easily. I mean, it's not very difficult to do it in experiment. Okay. I don't think so. So the single kick, I mean, just in any location, will not give you a second mode unless system is already has some imperfections and somehow this kick of mine is associated with another kick somewhere else and that creates second one. Something like that. Or maybe it's not exactly this system that I dealt with, but maybe it was something else, but I idealized differently. But the main thing is as follows, that the first load already, so to say, is the death of the column, so to say. I mean, this column, okay, this column buckles at this value. So we do not have to go and see exactly what happens at second load, etc. Naturally, that at this load there is a big displacement. Big displacement means that my differential equations that I wrote may be unapplicable because they were good for small deflections. So therefore, all these conclusions are really in error. Because mathematics is a model, naturally. Mathematics does not always describe exactly the world as it is. Because I have to use some differential equation. I used a linear differential equation. But displacement is big. So that may mean that my differential equation